Hello everyone, sequence series and proof, day number 3. Topic for the video is the MacLaurin series, how to build one, as well as evaluating limits using these series. Let's get started. Okay, so what is a MacLaurin series representation of f of x, and how is it used? Let's talk about that. So a MacLaurin series called p sub n of x is a polynomial of degree or order n representing a function f of x at the point x equals 0. And I really should put in here as well around x equals 0. For many functions, we can represent that function using a polynomial of degree n, as noted here, to model that function on an interval that we will find later on in this course. So we're going to use f of x. F of x could be any function. It could be e to the x, cosine x, sine x, arctangent. It could be anything. We're going to represent it using a polynomial. So the terms over here in general form represent our polynomial p sub n of x, right? That's an nth degree polynomial. So what we want to do is we want to make sure that f at 0 is equal to p sub n at 0, that the derivative of f is equal to the derivative of the polynomial, and so on and so forth, all the way down to the nth derivative. So what we're going to do is we're going to do a little evaluating. We're going to build this general form, and we're going to use it in the slides to follow. So f of 0. Well, f of 0 would equal a of 0, or a sub 0, I should say. Right, as I plug in a 0 for every x, all terms except for that constant term will disappear. So let's find the derivative of f of x. Well, a sub 0 drops. We would get 1 a sub 1. Our next term after that would be 2 times 1 times a sub 2 x to the first, plus 3 times 1 times a sub 3 x to the second, all the way out to the nth term, which will be n times 1 times a sub n times x to the n minus 1. Now you might ask yourself, why are you putting those 1's in there? You'll see in a few minutes. Okay, so f prime we wanted to evaluate at 0, and we want that the derivative of f at 0 is equal to the derivative of p sub n of x at 0. So if I plug in a 0 for all x's, everything disappears except for 1 times a sub 1. Okay, let's find the second derivative. We're going to use this again to help us to formulate the general form for an nth degree polynomial representing f of x. Second derivative, a sub 1 disappears. We get 2 times 1 times a sub 2. The next term becomes 3 times 2 times 1 a sub 3 x to the first, all the way out to n times n minus 1 times 1 times a sub n times x to the n minus 2. So the second derivative, evaluated at 0, comes out to be 2 times 1 times a sub 2. Okay, let's go up to the third derivative. Taking the derivative of the second derivative, I get 3 times 2 times 1 times a sub 3, plus all the way out to the nth term, which will be n times n minus 1 times n minus 2 times 1 times a sub n times x to the n minus 3. So the third derivative, evaluated at 0, will be 3 times 2 times 1 times a sub 3. Now, what's the point of all of this? It's to isolate and find out what a sub 0 equals in terms of f of 0. So a sub 0 equals f of 0. A sub 1 equals f prime at 0 over 1. A sub 2 is equal to f double prime at 0 divided by 2 times 1. A sub 3 is equal to f triple prime at 0 over 3 times 2 times 1, all the way out to a sub n. A sub n is going to equal the nth derivative evaluated at 0 over n times n minus 1 times n minus 2, all the way down to 1. Now, how would we define the denominator here? Well, it's going to equal n factorial. So what we're able to do with this now is we're able to substitute in for a sub 0 all the way out to a sub n and write a general formula for the MacLaurin series for f of x as the nth degree polynomial. We will take a sub 0, which is f of 0, plus a sub 1, which ends up being f prime at 0 over 1 factorial times x, plus a sub 2, which ended up being f double prime at 0 times x squared over 2 factorial. And we're going to continue this pattern indefinitely. And we could come up with the nth degree polynomial by finishing it x to the nth over n factorial. This gives us a formula such that we can come up with a polynomial representation for any function to any degree. Okay, so let's write this actually in sigma notation. Let's go from n equals 0 up to infinity. This would be a representation of f of x. F of x will be approximately equal to the summation, which will be a sum of these terms, which will be the nth derivative evaluated at 0 times x to the nth over n factorial. So f of x can be represented by a series. Okay, if I wanted the third degree polynomial, okay, which wouldn't be equal to f of x, but would be an approximation, I would just go from 0 up to 3. If I wanted the 13th degree polynomial, I would go up to 13. All right, let's use this on our next slide with a practical example. Okay, the granddaddy of them all. We're going to start with e to the x. And the main reason for that is because it's easy and because it's pretty simple to see things come together. So we want to find the third and sixth order McLaurin polynomial for e to the x. So the third degree polynomial will be p3 of x. The sixth degree polynomial will be p sub 6 of x. All right, so that means I'm going to have to take derivatives 6 times. So recall that p sub n of x is f at 0 plus f prime at 0 times x plus f double prime at 0 x squared over 2 factorial all the way out to the nth term, which will be the nth derivative at 0, x to the nth over n factorial. So in this case, I want to go out to 3 first. So f prime, why I love e to the x? Well, we all know why we love e to the x. Everybody knows that. Very easy to use in a calculus sense. Okay, so I went out to the third derivative. Now I got to find f of 0, f prime at 0. Well, f of 0 is 1. F prime at 0, oh, 1. F double prime at 0, hey, 1. F triple prime at 0, hey, 1. Very cool. So the third degree polynomial, p sub 3 of x, representing e to the x, is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, outstanding. Now, let's take p3 of x, p sub 3 of x, and let's write it in sigma notation. Okay, so we're going to go up to the third degree term, we're going to start at n equals 0, and we're going to write this as x to the nth over n factorial. Now, if you want to, you can see how that comes together. So if I plug in a 0 for n, this will become 1 over 0 factorial. And something weird that I think someone made up along the way is that 0 factorial is equal to 1. So if I plug in a 0, I get x to the 0, which is 1 over 1. That's 1. If I plug in a 1, I get x to the first over 1 factorial, which is x. If I plug in a 2, I get x squared over 2 factorial. Boom. If I plug in a 3, that's x cubed over 3 factorial. Done. Okay, now, p sub 3 of x is an approximation of e to the x. It's not an exact equation, right? Those are not equal. Now, p sub 6 of x will be a better approximation of e to the x. So let's construct the 6th degree polynomial for e to the x. Let's continue with our derivatives. Let's see, I gotta get back to my black pen here. Now, once I hit the 4th derivative, typically I don't use hash marks. But as you can see, this is pretty redundant with e to the x. So the 4th derivative at 0 is 1, 5th derivative at 0 is 1, 6th derivative at 0 is also 1. Let's build the 6th degree polynomial. So the 6th degree polynomial would be the 3rd degree polynomial plus a few more terms. So here's our 6th degree polynomial. 1 plus x squared over 2 factorial, x cubed, 3 factorial, x to the 4th, 4 factorial, x to the 5th, 5 factorial, x to the 6th, 6 factorial. Okay, now p sub 6 of x is going to be the same sigma notation from n equals 0, but now up to 6. But what I want you to be very, very aware of is that there's not 6 terms in the series because we started n equals 0. So since we started n equals 0, there's 7 terms, but the highest term's degree is the 6th power. Okay, so now what I want to show you is how this compares to our graph of e to the x. So let's say here we got e to the x. And earlier I mentioned that the 6th degree polynomial would be a better representation of e to the x around 0 than the 3rd degree polynomial. Let me show you how that would work. Okay, so this is the point 0, 1. The 3rd degree polynomial would have some n behavior that would be down to the left, up to the right. So, and this isn't perfect or to scale by any means, but a general representation of the 3rd degree polynomial would look like that. Now on this interval from, let's say, here to here, it looks like the green graph matches the black graph pretty well. Now the 6th degree polynomial, of course, will open upward on both ends, and it will follow that graph of e to the x in a much larger interval of what we call an interval of convergence. Right? It matches that graph for a longer period or a wider interval. So it's a better match. It's a better way to approximate the function e to the x further from 0. But they're both exact at 0 and for a pretty good interval around it. Okay, let's look at cosine of x on the next slide. Okay, it says find the 4th degree or order and 6th order McLaurin polynomial for this function given below, which is cosine of x. Let's find p sub 4 of x and p sub 6 of x. All right, so derivatives, here we go. G prime, I'm just going to find the first 6, will be negative sine. G double prime, negative cosine. G triple prime, that'd be positive sine. 4th derivative would be cosine. 5th derivative would equal negative sine. See how we're cycling around here back to where we started, which would be a negative cosine of x. Okay, so g at 0 is 1. G prime at 0 is 0. G double prime at 0, negative 1. Third derivative at 0, 0. Fourth derivative at 0 is positive 1. You can see we've got an alternating series here. Fifth derivative and sixth derivative. Okay, so we've got 1, 0, negative 1, 0, positive 1, 0, negative 1. That tells us here that what will be the linear term, the cubic term, and the quintic term will all not exist because the 0 coefficient will negate those terms. That means that cosine will only contain even-powered terms. It is not coincidental, that cosine is an even function. So let's construct the, the fourth degree or fourth order polynomial. That'll be 1 minus 1x squared over 2 factorial plus 1x to the fourth over 4 factorial. There is the fourth degree polynomial. Now let's put this into sigma notation. Okay, now how many terms do we have here? We have 3 terms, the highest of which is x to the fourth. So I'm going to go from n equals 0 up to n equals 2. Now we have an alternating series, so we need an alternator. That would be negative 1 to the nth power, which would make the first term positive, second negative, third positive. Okay, I'm going to multiply by x to the 2nth. That will make each of the powers even, starting at 0, then 2, then 4. And then the denominator will be 2n factorial. That will give us the fourth degree polynomial for cosine of x. So cosine of x is approximately equal to the fourth degree polynomial. Okay, let's construct the sixth degree polynomial, which will just be a couple terms beyond the fourth. And actually, it'll just be one term beyond. So p sub 6 will equal 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. Of course, the summation or sigma notation representation for that polynomial will be very similar. We're just going to add a term, go out to the third index, same alternator, same general term. This is called the general term. And therefore, cosine of x is approximately equal to p sub 6 of x. Okay, let's see what it looks graphically, what it looks like. All right, so cosine kind of looks like this. Not a perfect representation. It's about as good as I can do for now. 0, 1, fourth degree polynomial. You'll see that the fourth degree term, which is right here, is positive. Therefore, its coefficient is positive. Therefore, it will open upward. So I could see the fourth degree polynomial maybe looking like this. Symmetric about x equals 0. And then let's see, the sixth degree polynomial, its leading term, even though it's not in standard form, would be negative. Its coefficient is that, for that matter. So its polynomial graphically would probably look something like this. But as you can see, of course, the interval of convergence for the fourth degree polynomial would be slightly smaller than the interval of convergence for the sixth degree. Now, again, this is an estimation by my standards. The graphs could look slightly different, so don't judge me based on that. But as the number of derivatives start to match from the function cosine of x to the polynomial, the wider the interval of convergence. Now, some functions, and we're not getting into this in this chapter, but some functions have an infinite interval of convergence based on the fact that you can just keep going out term after term after term. It'll become more accurate for a wider interval. Others have a restricted interval. That's something that we'll talk about in our optional chapter next. Okay, let's look at a few more examples. Okay, let's write the first four non-zero terms of the McLaurin polynomial for the following function, h of x, which equals e to the x times cosine of x. So what do? Well, e to the x is approximately equal to 1 plus x squared over 2 factorial, x cubed over 3 factorial. I'm going to go out one more term, x to the fourth over 4 factorial. Now that will continue. However, I only want to go out far enough such that I will have 4 non-zero terms. I hope I went far enough. We'll see. Okay, cosine of x will be 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. I'll go out one more term to negative x to the sixth over 6 factorial. So what we're going to do is we're going to do a massive expansion of these two. So first, let's find 1 times 1, right? We're just multiplying these together. So h of x will equal each of the terms multiplied by the other. So I'm going to start with 1 from cosine of x times each of the terms. Let's go out to let's just expand out all 5 terms. So we're going to multiply 1 by e to the x, which comes out to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Okay, so I multiplied everything by 1. Now let's multiply everything by negative x squared over 2 factorial. This one to be precise. So we're going to multiply this by 1x squared over 2 factorial and x to the third over 3 factorial. Let's see what that gets us. Okay, so I get, let's see, negative x squared over 2 factorial. And again, I'm going to add these terms together. Negative x squared over 2 factorial minus x to the third over 2 factorial minus x to the fourth over 2 factorial times 2 factorial. We'll go out one more, minus x to the, what would that be, fifth, right? X squared times x cubed over 2 factorial, 3 factorial. Okay, so let's look at this and see if we're going to have to go further in either direction, right? Either, by that I mean, well, we have to go out to this next x to the fourth term and multiply that by multiple terms of e to the x in order to get a full expansion or a full simplification of the first 4 non-zero terms. So let's look at them. Okay, so let's see what we get here. So if I added this up, the 1, there's no common common factor. The x, no common factor. The x squared over 2 factorial, those actually reduce. So I'm going to then add the x cubed terms. So that is x to the third over 6 minus x to the third over 2, which is really 3x to the third over 6. So that will reduce, the x squared term disappears, the cubic term becomes negative 2x cubed over 6, which is negative x cubed over 3. So I'm going to have to go out to the 4th degree terms. Okay, and in this case, those are going to be these two terms combined. I won't need that 5th degree term right here. Okay, I'm not going to need this term because the 4th degree term will satisfy 4 non-zero terms. So that'll be x to the 4th over 4 factorial minus x to the 4th over 2 factorial, which is 4. Now, however, I do have to account for this, and I want you to be aware of this. There would be one more x to the 4th term if I multiplied x to the 4th over 4 times 1. So I'm actually going to add that, x to the 4th over 4 factorial. Okay, so let's combine these together. This would be x to the 4th over 24 minus 6x to the 4th over 24 plus x to the fourth over 24. So that'd be negative 4x to the fourth over 24, which will be negative x to the fourth over 6. So there you have it. H of x, first 4 non-zero terms. This would be the fourth degree polynomial representation of h of x. All right, let's look at x cosine 2x. Okay, this is really interesting. Okay, but what I'm going to do is I'm going to take x, which is equal to itself. There is no MacLaurin series for x. It is just x. But cosine of 2x, instead of coming out and taking a bunch of derivatives, I'm going to take cosine, the shell of cosine. And what I'm going to do is in the parenthesis, I'm actually going to plug a 2x. And I'm just going to go out to the 6th degree term. All right, and in there, instead of doing all that work, I'm going to plug a 2x. All right, so I'm going to take, to find t of x, I'm going to take this x right here and multiply it by the series that I get when I expand cosine 2x, which would be 1 minus 2 squared x squared over 2 factorial plus 2 to the fourth x to the fourth over 4 factorial minus 2 to the sixth x to the sixth over 6 factorial plus a bunch of stuff if I were to go far enough out. But I have 4 terms here. That's all I'm going to be worried about. T of x will then be x minus, and I'm going to reduce. This would be 2x squared plus, that'd be 16 over 24, which is 2/3, 2x to the fourth over 3, minus, that'll be 64 over 720. I'm not going to try to reduce that, so I'm just going to leave it as 64x to the 7th over 720. Now, I did mess something up back here. Forgot to multiply these terms by x, which would make those terms cubed and to the 5th. Okay, there is the first 4 non-zero terms, which constructs the 5th degree polynomial representation of x cosine 2x. Okay, let's keep moving on a couple more examples. All right, it says find the MacLaurin series, including the general term for each function. Now, the general term is going to have an n in it. And the general term is very useful when constructing sigma. So f of x, instead of taking derivatives like we've done before, I'm going to take the shell of e to the x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial out to the general term. The general term will be very useful, and you'll see why in just a moment. I'm going to plug in an x squared. Okay, and then we're just going to simplify. So the f of x will be approximately equal to 1 plus x squared plus x to the fourth over 2 factorial, x to the 6th over 3 factorial, out to the general term, which will be x to the 2nth over n factorial. That would be the nth degree polynomial representation. So p sub n of x is an approximation of f of x, but would be equal to the sum from n equals 0 all the way up to whatever term we want it to be. Okay, so in this case, nth term of x to the 2nth over n factorial. Now, this is really cool, you guys, because the general term, as long as you write it correctly, is your inner portion of your sigma notation. Okay, let's scroll down here and look at arctangent of x. So before we get into arctangent of x, I want to talk a little bit about infinite geometric series that, by the way, converge. Okay, so if I went from n equals 0 to infinity, and I said that this series converged, the first thing you should think is a geometric series that has a common ratio between -1 and 1. Okay, so if I took, let's say, x to the nth, okay, and we wrote out all the terms, we would assume that x is between -1 and 1, right, in order for this to be convergent. So if I laid out the terms, I'd get 1 plus x squared plus x cubed, all the way out to the general term x to the nth. So how would I write the summation? Well, the sum, or the infinite sum, would be the first term over 1 minus the common ratio. Okay, so minus x. Now, let's assume for a moment that we had a function, right? Let's call h of x 1 over 1 plus x. That looks very, very similar, right? Very similar. So if I rewrote h of x as 1 over 1 minus a negative x, we could see that the common ratio in this case would be negative x. So the summation here from n equals 0 to infinity would just be negative x to the nth power, which of course would be 1 minus x plus x squared minus x cubed, and so on. It's an alternating series. Okay, now that allows us to say that 1 over 1 plus x is approximately equal to 1 minus x plus x squared minus x cubed plus x to the 4th minus blah, 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 and we could continue going. This right here is the MacLaurin series for h of x, right? This is an approximation. Actually, I should say equal to 1 over 1 plus x, which is approximated by that series. Okay, now I'm going to take a step. You might not feel comfortable with it, but I don't care. So g of x, let's actually say, is 1 over 1 plus x squared. Well, how would I work that into this MacLaurin series? Well, I'd just plug in an x squared for every x. That'd be 1 minus x squared plus x squared squared minus x squared cubed plus x squared to the 4th, and so on. All right, so as we look at that, how is arctangent related to 1 over 1 plus x squared? Well, it just so happens to be the integral of 1 over 1 plus x squared. So arctangent is equal to the integral of the green series that I have below. Oops, x to the 6th, and so on. I'll go out to, let's go out to the general term, which would be x to the 2nth. All right, so here's my 0 term. Here's my first term. Here's my second term, and so on. So we're going to go out to x to the 2nth. If I integrate that, that should be equal to arctangent of x. Well, that would be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 6th over 6, all the way out to x to the 2n over, 2n plus 1 over 2n plus 1. And there you have it, guys. There is the MacLaurin series for arctangent of x. Absolutely awesome. Now, I have had somebody in the past say, well, shouldn't there be a plus c? That's a indefinite integral. You're absolutely right. But what is the arctangent of 0? Well, it equals 0. Therefore, if we have 0 equals a bunch of zeros, plus c, right? C would have to equal 0 as well. Okay, we've got a couple of limits to do on the next slide, and that will be it for today's lesson. Okay, so how do we use these things called the MacLaurin series in order to evaluate limits? Well, first of all, you're going to have to get an indeterminate form. All right, so in this case, limit as x approaches 0 of 1 minus e to the x squared over 1 minus cosine of x. Well, I can clearly see that the limit as x approaches 0 of 1 minus e to the x squared will equal 1 minus 1. And the limit as x approaches 0 of 1 minus cosine of x will also equal 1 minus 1. Now, never, ever, ever should you ever put 0 over 0 anywhere. Okay, your credit will be lost. That's bad news. Don't ever do that. But just know that in your mind, you're thinking about that 0 over 0, right? You should know that that's there. Question it, right? Now what we're going to do is we're going to use a MacLaurin series for e to the x squared and for cosine of x. Okay, cosine of x I know is the following. And typically when you're evaluating a series, or excuse me, a limit, you typically don't have to go further than a couple terms, maybe 3. I would go out at least 3 terms just so that you can see what's going to happen within the series. Okay, and then e to the x squared I believe was 1 plus x squared plus x to the 4th over 4 factorial, over 2 factorial. And we'll go out one more term, plus x to the 6th over 3 factorial. And what I'm going to do is, since I know that this limit has an indeterminate form of 0 over 0, I'm going to rewrite the numerator as 1 minus that series. Okay, and I'm just going to go out like I have here to the 6th degree term in the numerator, but knowing that that continues on indefinitely. Okay, denominator will be 1 minus said series. And I'll just go out to the 6th degree term just because that looks nice. Okay, again, if I plugged in a 0, nothing would happen until I simplify. You always want to simplify after you do an adjustment within limits. So I'm going to simplify. Otherwise, you'll still get an indeterminate form. You'll see that as I subtract, the 1's reduce, and it changes the signs of everything else on the inside. Okay, so 1's reduce, changing the signs of every term after that. So I'm going to have the limit as x approaches 0 of negative x squared minus x to the 4th over 2 factorial minus x to the 6th over 3 factorial minus some other stuff over x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, continuing on. Now again, I get 0 over 0, so I've got to do something else. What I'm going to do is I'm going to factor out an x squared, which will leave me with negative 1 minus x squared over 2 factorial minus x to the 4th over 3 factorial minus a bunch of stuff. Denominator, same thing, factor out an x squared. That leaves me with 1 over 2 factorial, which is 1/2, minus x squared over 4 factorial, plus x to the 4th, over 6 factorial, minus a bunch of stuff. So the x squareds will reduce. So in essence, what I have is the limit as x approaches 0 of negative 1 minus x squared over 2 factorial plus x to the 6th over, x to the 4th over 3 factorial minus some stuff over 1/2 minus x squared over 4 factorial plus x to the 4th over 6 factorial minus some stuff. Now what happens when I plug in a 0 to all the terms containing an x? They're gone, right? Here you go. So I get negative 1 over 1/2, which actually comes out to be negative 2. Therefore, this limit is equal to negative 2. Let's look at one more example here. Looks like I'm going to be working with e to the x. Love it. Right, I can see clearly that the limit as x approaches 0 of e to the x minus e to the negative x will be 1 minus 1, which is 0. Limit as x goes to 0 of x will also be 0. E to the x, its McLaurin polynomial would be 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial. I'm going to stop there. E to the negative x, let's do that in a different color. E to the negative x. If I plug a negative x in for every x, I'll get an alternating series. All the odd terms will be the negative terms. Okay, and so on and so forth. Therefore, this limit, of course, which would be an indeterminate form. In your brain, you're seeing an indeterminate form, right? 0 over 0. Don't write it on the paper or on the iPad. Don't do it. E to the x minus e to the negative x will be the green series minus the purple series. So that'll be 1 plus x squared over 2 factorial plus x to the 3rd over 3 factorial and a bunch of stuff minus 1 minus x plus x squared over 2 factorial minus x to the 3rd over 3 factorial plus some stuff all over x. So as we combine like terms, we'll see that 1 minus 1 reduces, x squared over 2 factorial reduces, and we're going to be left with only odd terms in the numerator. Excuse me, terms of an odd degree. So I'll have x minus a negative x, which makes 2x. X cubed over 3 factorial minus a negative x cubed over 3 factorial, which will be plus 2x cubed over 3 factorial. If we were to continue, we would get 2x to the 5th over 5 factorial, and so on and so forth, all over x. So what we want to do next, and of course we want equivalence along the way, is I'm going to factor out an x, leaving me with 2 plus 2x squared over 3 factorial plus 2x to the 4th over 5 factorial all over x times 1. Okay, as you can see, very similar to the last problem, the x's reduce. And formally, I should write this out and be a good teacher, so I'm going to. So the limit as x approaches 0 will then be of 2 plus 2x squared over 3 factorial plus 2x to the 4th over 5 factorial, and on and on. Now these terms after here become insignificant, right, because they'll all contain x's. And as x approaches 0, all terms will approach 0 except for the first, which gives us a limit of 2. All right, guys, that's it for day number 3 on the MacLaurin series, building one as well as evaluating limits. We'll see you in the next video.